Today we're going to look at topic 3.3, the factor theorem, in Math 2030-1. So the factor theorem states that if x minus a is a factor of our polynomial, if and only if the polynomial evaluated at a is going to be equal to 0. What does that mean? Let's have a look. Let's look and see if x minus 1 and x minus 2 are factors of our polynomial p of x equals x cubed minus x squared minus 5x plus 2. So the root of x minus 1 is going to be 1. So we're going to say p of 1 is going to be 1 cubed minus 1 squared minus 5 times 1 plus 2. Well, that's equal to negative 3. Therefore, p at 1, or x minus 1, is not going to be a factor. Now let's look at x plus 2. So that means I'm going to have to evaluate it at p at negative 2. P at negative 2 is negative 2 cubed minus negative 2 squared minus 5 times negative 2 plus 2, and that is equal to 0. Therefore, x plus 2 is going to be a factor. That's how that works. If we looked at a graph, we can see that the roots are going to be at negative 2, positive 1, and positive 2. That tells me that the factors of this polynomial are going to be, there's zeros at negative 2, 1, and 2, and the factors are x plus 2, x minus 1, and x minus 2. In example 1, use the factor theorem to test for factors of a polynomial. P of x is x cubed minus 3x squared minus x plus 3. The question is, which binomials are factors of this polynomial? And there's 4 to test. Because the factors of our last term 3 are going to be positive 1, negative 1, positive 3, and negative 3. So here we go. X minus 1. Well, that means that p at 1 is going to equal 1 cubed minus 3 times 1 squared minus 1 plus 3, and that's going to work out to be 0. So yes, that means x minus 1 is a factor. In the second one, x plus 1, if we evaluated it, we also are going to get 0. So yes, x plus 1 is also going to be a factor. In our third one, p at negative 3, we're going to get negative 27. Minus 3 times negative 3 squared is a minus 27. Minus plus 3 and plus 3 is going to give me negative 48. So the answer is no. X plus 3 is not a factor. Lastly, x minus 3, if you plug in p at 3, you're going to end up with 0. So yes, x minus 3 is a factor. So since this is a cubic function, our leading coefficient, our leading power is 3. That means there's going to be 3 roots. We found all 3. So one possible equation could be p of x is equal to x minus 1 times x plus 1 times x minus 3. Although it's going to take further investigation to prove that that is in fact our equation. In the integral zero theorem, this states that if x minus a is a factor of our polynomial function, then a is a factor of the constant term of our polynomial. That has implications to help us. We're going to factor this polynomial using the zero theorem. 2x cubed minus 5x squared minus 4x plus 3. So we're going to look at the last term, the constant term 3. If we can find factors and test the factors of 3, we will see if it's going to be factorable by any of those. Step 1 is to find the factors of 3, which are positive and negative 1, positive and negative 3. Because 1 times 3 is 3, and negative 1 times negative 3 is 3. So p evaluated at 1 is going to give me negative 4. So obviously x minus 1 is not going to be a factor. p evaluated at -1 is going to give me 0. So that tells me that x plus 1 will be a factor. Step 2 is going to divide this polynomial by x plus 1 to break it down further. If we use our short division from yesterday, you're going to see that -1 divides into 2, -5, -4, and 3 because our remainder is 0. Now we can say that it's going to be our polynomial divided by x plus 1 is going to be 2x squared minus 7x plus 3. Now our next step is to further factor 2x squared minus 7x plus 3. We have to do that by decomposition, which means that we have to break the middle term down, -7x, into -6x minus 1x. Then I can take the greatest common factor out of the first two terms, which is 2x, and divide it, and I get x minus 3. Now I can factor a -1 out of the next two terms to get -1 times x minus 3. So fully factored, it's going to be x minus 3 times 2x minus 1. So there I have found the other two factors. So altogether, fully factored at the top, it's going to equal x plus 1 times x minus 3 times 2x plus 1. Your turn is to fully factor x cubed minus 4x squared minus 11x plus 30. You can do that on your own by stopping this and then continuing, and you'll find that if we cheat it a little bit, graphed it to find the roots, we can see that one of the roots is at x plus 3 because it's going to be at -3. Fully factoring, then we're going to see it's going to be x plus 3 times x minus 5 times x minus 2. So as you can see, we can fully factor large polynomials using several tools, one of which is the factor theorem. Another one is called the integral zero theorem, and by using our graphs to find the roots. And a little cheating there. Factor higher degree polynomials. Let's do a factor x to the 4th now, minus 5x cubed plus 2x squared plus 20x minus 24. So we're going to have to find factors of -24. Well, we can start with +1 and -1. And if we did that, the p evaluated at 1 is going to be, well, it's not going to be 0. If I did p at -1, 1 plus 5 plus 2 minus 20 minus 24, and that one's not going to be 0. But when I evaluate p at 2, I get 16 minus 40 plus 8 plus 40 minus 24. That is equal to 0. So now I can take my original polynomial and divide it by 2. So 2 goes into 1, -5, 2, 24, 20 and 24. And when I use short division, speeding this up a little bit, I'm going to end up with x minus 2 times x cubed minus 3x squared minus 4x plus 12. Now what we have to do is start all over again with the x cubed minus 3x squared minus 4x plus 12. So you're going to have to look at the 12 and say, how do I factor the 12? Well, the first two that I can put in there are +1 and -1, and see if I can figure out anything from that. So p at 1 is going to give me not equal to 0. P at -1, that's not going to equal 0. P at 2 again does equal to 0. So now I can use my short division and divide +2 into the polynomial with 1, -3, -4, and 12 as coefficients. As you can see, bring down the 1. 1 times 2 is 2. Add up the second column, I get -1. 2 times -1 is -2. Add up the third column, I get -6. 2 times -6 will be -12. And when I add up the last column, I get my remainder of 0, which means it's going to go into it evenly. Therefore, I can now say that my polynomial is going to be x minus 2 times another x minus 2 times what's left here, which is x squared minus x minus 6. My last step is to now factor the x squared minus x minus 6, which that I can use the sum product method on. So now that's going to break down into x minus 3 times x plus 2. And when I bring down the x minus 2 times the x minus 2, I'm ready to write it in its final form. Notice that I have two x minus 2's, so I'm going to say this is equal to x minus 2 squared times x minus 3 times x plus 2. There's my final answer. In B, we start again with the factors of 18. I find that p at negative 1 is equal to 0. So now I can say that x plus 1 is going to be a factor of this. And I can divide negative 1 into 1, negative 3, negative 7, 15, and 18. And when you finish all this up, you're going to end up with the long process of getting x plus 1 times x plus 2 times x minus 3 squared. So your assignment is to do page 133, 1AC, 2ACE to 7ACE, 8, and 11. That's for day 1. And for day 2, you're going to be doing 1BD, 2BDF to 4BDF, 5BD to 7BD, numbers 9, and numbers 12.